Today we're going to talk about multiplication and the different ways to solve when we are multiplying whole numbers. So in the past, you've learned how to multiply whole numbers, and one way is called an area model. This is also considered like an array. And here, when we use the area model, we are breaking up the number into parts and pieces so that we can multiply numbers mentally. So if I had the problem 3 times 1,125, I can break up the bigger number into its pieces based on place value. So I know I have a 1,000, a 100, a 20, and a 5, and I can use that and multiply that all by 3. So making an area model allows me to chunk out those pieces and say, okay, I'm going to multiply that 3 by 1,000. I'll eventually put my answer in that box. And I will multiply that 3 by 100. It's like I'm doing expanded form up here on the top. And then I have, so the 1,000, the 100, now it's the 20. And then I am going to have the 5. So expanded form of this number down here. And when I multiply, I can do that mental math of, okay, well, I know 3 times 1 is 3, and each of these digits is a 0, so I can simply use those as placeholders because they each represent a 10, like we've learned. So 3,000 is this partial product. So this is part of the product. We don't have the whole thing yet because we've only technically multiplied the 3 times the 1,000. So 3 times 100, using that same strategy of 3 times 1 is 3 and having those two zeros. 3 times 2, 6, and the 0, so 60, and then 3 times 5 is 15. So because I did that, I can still see all of the place value that's in this number, and I've for sure multiplied the 3 by all of the place values, and I was still able to do mental math. Now the thing with this is now I have a lot of partial products that need to be added together. Sometimes this is easily done mentally. In this case, I would say it is because I just can look at the place values as we go down. We have to be careful of placeholders or anything that might eventually carry when we add. So I'm still going to demonstrate that there are going to be times where you have to visually see all of these being added together, even though that can be done mentally. So when I add them all together, I get a final product of 3,375, right? I know this is a reasonable answer. This is a logical answer, because if I think in my head that, okay, this is about, I'm going to think, okay, well, yeah, this is a 3. That's easy to think about. And I'm thinking about, okay, well, this, I can think of it, that's pretty close to like 1,000, right? So if I put those thoughts together here and I mentally think about 3 times 1,000, well, that equals 3,000. Is my answer reasonable? It is. So it's not always going to be an exact, but I'm estimating to think about what would be my roundabout answer. This is a big life skill of knowing how much you're spending and how much money you should have back. You're estimating those answers. So area model is one way we can show how to multiply larger numbers. Now, another way we can do that is using partial products still. So sometimes people call it just partial products, when really it's always partial products. We're always going to have parts of a product and then be putting them together. So if I still have that same number, I'm going to take the 3 times 1,125, and I'm going to set it up like a standard algorithm problem where it is lined up with the larger number on top and I am going to multiply the 3 by all the pieces. It's easier to always multiply the smaller number into the bigger number visually by place value, and then that way you know you've made sure you multiplied all the pieces. So the first thing we can do is multiply the 3 times the 5. So mentally what's happening, I'm going to write off to the side. So 3 times 5 is 15. Great, got it. Then we are going to continue like stacking all of these different partial products. We haven't multiplied the 3 by everything yet. So just like we did with the area model, we're going to multiply all of the parts and pieces. So now I'm going to multiply the 3 times the 20, right? So 3 times the 20 was 60. So I'm going to put my thoughts off to the side here. 3 times 20 is that 60. And then I'm also going to multiply the 3 times the 100 and get 300. Keeping all my place values in line here is important for when I go to add them. And then the last one I'm going to multiply is that 3 times the 1,000. So that would be 3,000. So all lined up in place values. And then I'm going to add them together. So I still have that 5, 7, and then 3, and a 3. So 3,375. So in this case, I did exactly the same thing. Look at my partial products from the area model. They're exactly the same. So the only difference is from area model versus partial products, box. So we either have it in a box or we're just stacking it, okay? And I'm just using those color codings so you can see the different steps that are happening there. Well, now what we're going to do here in 5th grade is we're going to put this all together. So partial products this way really shows all of the place values. So we are using these zeros to make sure that our 3 and our 6 is all in the right spot. So another way is called the standard algorithm. This is the way all of us adults were taught, and it is where we take our, let me write standard, so it's standard algorithm, okay? It's the quickest way to multiply whole numbers. And really it's because you're cheating the place value system. So if I have 3 times 1,125, I'm still going to stack it like we did with the partial products and put the 3 underneath, okay? And I'm still going to multiply 3 by all of these pieces, but I'm not going to think of them as 20 or 100 or 1,000. I can think about it as a single digit because of where I put my partial products, okay? So I'm going to still use my color coding here so you can see it relate to the partial products we did earlier. So 5 times 3 is what again? 15. So I put the 5, and instead of putting the 1 down here, I'm going to carry it. So it's still in the tens place as it would be down here. And this time I'm going to continue multiplying and putting my product in one line. So now I'm going to do the 3 times the 2. Now, before we thought of it as a 3 times 20, but we can, with standard algorithm, we can look at it as just an individual digit. 3 times 2 is 6. Now, we still have this 1 to consider, so we're going to add those together. So 3 times 2 is 6 plus 1 is 7. Okay, so we now have our 7 there. Nothing carried because it was just one digit. So now we are going to multiply the 3 times the 1. Now technically it's a 100, but we don't have to use those zeros for the 100 because look, we're already in the hundreds place. So 3 times 1 is 3. And then our last thing to multiply is that 3 times the 1,000. Again, look, we're already in the thousands place, so we don't even need the 0 placeholders. So 3 times 1 is 3. So all in one shot, we have the product that we ended up with when we did the partial products. So you can see where the 15 and the 60 changed because we already added that 1. So do you see how these were going to be added together anyways? That's what was happening here. And we still got our same answer. Okay, let's try it with another one using that standard algorithm. And this time we're going to do a number that carries much more, so that way we can see that different adding happening in our problems. So let's go ahead and do a challenging 9 times 436. Okay. So again, we are going to put the larger digit number up on the top. So there's more digits than the 9, and lining up the 9. Okay, so we're going to think of this standard algorithm again, just multiplying the digits and not having to worry about the place value. So we're going to multiply 9 times 6 first, and that is 54, carry the 5. So I didn't write the 5 here, I wrote it in the next place value. And then we are going to multiply the 9 times 3, and 9 times 3 is 27. So I'm going to write a note, so just for you guys to know where this is coming from. 9 times 3 is 27, but then I have to add the 5, right? So it is going to be a 32. So my 27 plus the 5 from here gave me a 2, carry the 3. Okay, see the 32? And then we are going to have 9 times 4. And that we'll use, let me get my color here. So 9 times 4, I'm going to write this one off to the side again too for you to see. 9 times 4 is 36. 9 times 4 is 36. So we have to also add the 3, and then that means we have a 39. Okay, so here's 39 for our final answer. Now, let's think of this one as reasonable. So 9 times 400, you could think of that. So our estimating here would be 400 times 9. I always pick the numbers that I can easily multiply. So that equals 9 times 4 is 36, but then I have the 2 placeholders. Our answer is reasonable, right? So we use the estimating to check to see. Okay, so we can carry and skip the place value, so that way it's easier and quicker to multiply. But now what if we use numbers larger than 9? Let's try something like that. So numbers larger than 9, let's try 16 times 28. Okay, and I'm actually going to show this in 2 different ways. I'm going to show it in a partial product way, and I'm going to show you the standard algorithm way. So this will be the standard algorithm that we'll do, and then this will be the partial, and I'm going to abbreviate, products. Let's go ahead and look at our numbers. They both have 2 digits, so it doesn't matter which one goes on top or which one goes on bottom. So I'm just going to go with the way they're already written. Okay, for partial products, it's always written the same too. So I really want to compare and see how much more work and steps there are in partial products versus standard algorithm. So let's start with what you would already be more familiar with, that partial products. And let's multiply each piece by each piece. So we have 8 times 6 is 48. And then we have 8 times 1, but technically that's a 10 when we're thinking about partial products. 8 times 10 is 80. And then we would have a 2 times technically it's a 20. So 20 times 6 is 120. So see, we're still thinking about that place value of these digits. And then 20 times 10 would be 200. Then you can add those together and get your final product. 8 here, 8, 9, 10, 14. Carry that one, and then 3, 4. So 448, okay? So that's still partial product. So I had the 48 was from 8 times 6, 80 was from 8 times 10, and then this one we ended up doing the times the 2. So, but technically it's a 20. So 20 times the 6, and then the 20 times the 10 to get all of our partial products. So let's see if our standard algorithm in the steps, how they compare to this. So I'm not going to think of the place value that each of these digits in, and I'm going to do my carrying instead of putting all the parts. So 8 times 6 is 48. So I'm going to carry my 4, see my 48. And then I'm also going to do the 2, or not the 2 yet. I'm still going to do the 8. So 8 times 6 is 48. So 8 times 1 is 8, but then I have to add the 4. So 8, 9, 10, 11, 12. I have 128. Okay. So technically what I just did there is I did 16 times 8. I bundled those together compared to the partial products. Now, if I'm going to multiply everything by this 2, I can't start in this place value. I have to actually put a placeholder so that I start as if I would if I was doing a 20. So remembering that placeholder is crucial because when you go to add, it'd be lined up incorrectly. So another thing is if I've carried something with my first partial product, I need to remember that I am not using that 4 again. So now I can start multiplying. I have my placeholder, I've crossed off anything that I've carried. And what am I technically going to be multiplying here? I'm going to be technically multiplying 16 times 20. But that 0 already being here, I won't have to worry about it. So 2 times 6 is 12. I carry the 1. See, it was important that I got rid of that 4 so I could see it. Never erase it. Always cross it off simply so we can look back at our work if needed. 2 times 1 is 2 plus the 1, so that would be a 3. So now I have my 2 partial products, and I can add them together and get 448. So seeing all the place value, more partial products, skipping the place value, using what we know about place value though, and still being able to multiply much quicker. So this is the method we will continue and perfect here in 5th grade and continue for the rest of our years in math. I can't wait to explore more with you.